Okay, so we're going to talk about measurements. Measurements are things you make, for example, in the laboratory when you measure a certain length or you measure the mass of something. Whenever you make a measurement, there's some inherent uncertainty in it, which goes with the type of instrument that you're using. Okay, so you'll be doing a lot of error analysis in your lab findings, and we'll be mainly talking about percentage errors. But before we get to that, let's talk a little bit about two things. One is accuracy, and the other is precision. So the accuracy is, let's say you have a known quantity. We know what the value should be. For example, of the acceleration due to gravity, we know its value should be 9.81 meters per second squared. And say you measure it in the lab, how close can you get to this value? That's a measure of your accuracy, okay? To how many significant figures are you able to measure? Are you just able to get the 9 correct or the 9.8 correct? Or you get all the 3 significant figures, 9.81 correctly? Okay. The other term is precision. That means how repeatable your experiment is. So how repeatable or reliable is it that you will time and time again get the same value or the same answer? So you'll find that whenever we do measurements in the lab, we take at least 3 readings for something so that we get an average that we can rely on, okay? That has to do with the precision of measurement. So we're going to do a problem, and let's see how we move forward. Okay, so here we are. In this example, we have a formula given at the top, which I put in for you. So the problem actually starts beneath, and it says a grocery store sells 5 kg bags of apples. You purchase 4 bags over the course of a month and weigh the bags each time. You obtain the following measurements. The first week, you get 4.8 kgs. Maybe feel a bit cheated. The second week, you get 5.3. Ooh, you've been compensated. Third week, 4.9. Fourth week, 5.4. You determine that the weight of the 5 kg bag has an uncertainty of plus or minus 0.4 kgs. What is the percentage uncertainty in the bag's weight? So first, let's talk about how did we get the plus or minus 0.4 kgs. Since we know that the value was supposed to be 5 kgs, let's see how far away each of these quantities are from 5. This is 0.2, this is 0.3, 0.1, and 0.4. So this has the greatest uncertainty, right? So that's where the 0.4 came from for the uncertainty. But it could have been 0.4 less or 0.4 more. So we're going to put a plus or a minus. We don't know. In either direction, there could have been an error. We know that the maximum error could have been of at least 0.4 kgs. Okay. What percentage is this 0.4 of 5? This is the question. So if you use this formula, the percentage of uncertainty equals the change or the error in measuring a quantity divided by the quantity itself times 100 in order to get a percentage, right? So in our case, this would be the 0.4, this would be 5. So 0.4 divided by 5 times 100. And what is that going to be? That's going to make 8%. So there's actually an uncertainty of 8% in the bags that are being sold. You may be off by 8% in whenever you get a 5 kg bag, okay? That's what you can determine by doing this. So every time you make a measurement in the lab, you are going to measure the possible uncertainty that you have. Let's say here you have this blue rectangle, and this long side of it, so its length is 16.3 centimeters, and the width is 4.5 centimeters as measured by you using a ruler. Now, if you look at the ruler carefully, you'll see that you can measure to an accuracy of 0.1 centimeters. So you could have 16.3, and then the next measurement would be 16.4. And the next smaller measurement would have been 16.2. They're all both off by 0.1 centimeters. So we're going to add to 16.3 a plus or minus 0.1 for the uncertainty. Since you use the same ruler here, you have the same uncertainty. You have 4.5 plus or minus 0.1. Okay. So if you were trying to find the area of this blue rectangle, which values would you take? You could have, let's say we do the negatives first. So we get 16.2, which is the lowest value of the length, times the lowest value of the width, which is 4.4. And that gives us an area of this much, 71.28 centimeters squared. Or you could err on the higher side and go to 16.4 times 4.6. It's going to give you 75.44. And then you could have different combinations in between where one is greater and one is lesser, and you're going to get some in-between number. Or you could go with the in-between average values of 16.3 and 4.5, forget about the error, and just write down the area as 73.35 centimeters squared. So you see how much difference it has created in the error in the area. So how do we say the area of this blue rectangle, the area of the blue rectangle for certain? We're going to say that we are only able to measure it accurately to two significant figures because we have two figures here, 4 and 5. So we need to give our answer to two places, which is 71, 75, or 73. And we are going to say we're going to take the 73 and add to it a plus or minus 2 centimeters squared error. Okay. So we could have gone from 73, 2 up to 75, or 2 down to 71. Hence the 2 centimeters squared error in measuring the area. Okay. So the answer has two significant figures because the smallest measurement, the least number of significant figures it had was 2, 4.5. We're going to do some more about significant figures. So a significant figure tells you the number of places or digits that you know reliably. Okay, like you measured 16.3, you might not have been sure if the line, if it wasn't exactly on the 0.3, you might have been tempted to say it's 16.4 or 16.2. So it's really the 1 and the 6 that were completely significant and known, and the last digit there was some uncertainty to it. Yeah, hence the 0.1 and the plus or minus 0.1 in the previous slide. In general, we're going to say that anything that you measure, if it's a non-zero value in a number, then it's always significant. So the question only comes if you're given a digit and the digit happens to be a 0. So if it's just holding a place, like say 0.052, then these two zeros are just holding a place. Then they are not significant, and this has two significant figures, which are 5 and 2. The easiest way to know this is to express your number in scientific notation, which means you would do 5.2 times 10 to the minus 2, so you moved your decimal by 2 places, and you put that in terms of a power of 10. So now you can clearly see that you have two significant figures, because whenever we do significant figures, we completely ignore the power of 10. Okay, so you only need to look at the number before it. Okay. So what happens when you actually multiply two numbers together, like we just did in the area, or you divide two numbers, okay? So in that case, the rule that applies is to use the lowest number of significant figures in the actual measurement that you had. So the known values that were given to you. For example, the length and the width. Since the width in our case had two significant figures, we reduced our area, which was the multiple, down to two significant figures. When you add and subtract, a different rule applies. You're going to stay with the same number of decimal places in that case. So you're not looking at significant figures, you're looking at number of decimal places. We're going to do a couple of examples, and hopefully that will make it more clear. So say I have a number here, 14.71 meters. This has 1, 2, 3, 4 significant figures because all of them are non-zero digits. And this number here, 7.46, would have then 3 significant figures. And now if I want to multiply them, remember the rule? The rule is I need to choose the one with fewest number of significant figures. That's this one. It has 3. So my result needs to have 3 significant figures, the answer that I give back. So if I multiply these two out in the calculator, I get 109.74. It's going to be meters squared because it's meters times meters. This has many more than 3 significant figures. This has 1, 2, 3, 4, 5 significant figures. I need to reduce this to 3. That means I need to get rid of 2 places. If I look at this place, it's going to round up this place when I get rid of it. So I'm going to go to 110, okay? And if I write that in scientific notation, it's 1.10 times 10 to the power 2. So that's how you came to this value. So whenever in physics you're doing a calculation, whether it's in your homework or anytime in the class, you're going to do your entire calculation, and when you come to an answer finally, you are then going to consider to what number of significant places should you report the result. If you don't consider this, then it becomes immediately apparent to somebody that you do not understand uncertainty in measurement, okay? So you always need to consider how many significant places do you report something to. Okay, here's the addition and subtraction. I want to add these two digits, these two numbers, 0.09 plus 0.91. Both of them have 2 decimal places. Hence, my result will also have 2 decimal places. So if you add these, you get 1. But you can't just write 1. You need to write 1.00. All these places are significant, 3, because you accurately know that these 2 places are 0. So sometimes zeros are significant and sometimes they are not. And that can be hard to determine. Okay, so here's the first number. How many significant figures do you think it has? Remember, you want to put it in scientific notation. It has 1, just this number, digit is significant. In general, if a number is given to you, like this one, including zeros, so it ends with a 0, then these are all significant. Okay, so this would have 1, 2, 3, 4, 5, 6 significant figures. The next one has just 1 significant figure. Here we have 1, 2, 3, 4, 5. And if a 0 is squished between non-zero places, then it's always significant. So you have 1, 2, 3, 4 significant figures here. Here are the answers, and you can check your answers. You should do this on your own without listening to me, using just the slides, and so that you get some practice in doing these. Rounding, I'm sure you've done before. Basically, when you decide how many significant figures you want to keep, you're going to look at the next digit, and if it's 5 or above, you're going to round up, and if it's below 5, you're going to keep it exactly as it is and just cut off. Okay. Orders of magnitude. Physicists love to talk about orders of magnitude. This means the power of 10 that applies. Okay, so if you're talking about the height of a human being, it's about 1 meter, 1 to 2 meters. So you're going to say a power of 10 to the power 1 is the order of magnitude for that. And if you're going to say measure much larger distances, you're going to talk about, is it 100 meters? Is it 1,000 meters? So you're talking about powers of 10. Okay, that's called the order of magnitude. So if the power of 10 is 3, then it's 3 orders of magnitude. If the power of 10 is 2, then it's 2 orders of magnitude, and so on. One of the things that you'll often have to do in your physics problems is to convert. Remember, we talked about units earlier in this chapter, and we want to always stay in NKS SI units, which are meter, kilogram, and seconds. But in a question, you might be given a question like 1 inch equals 2.54 centimeters. How many centimeters in 15 inches? Yeah. So then you're going to do 15 times so many centimeters, because there's so many centimeters in 1 inch. And algebraically, you can see that the inches cut out and the centimeters, all that remains. So your answer has to be in centimeters. So it's nice to write it out like this whenever you convert. So it's 15 times 2.54, you're going to get 38.1 centimeters. Okay. Estimate, whenever you're asked to make an estimate, essentially you are doing a order of magnitude calculation, so you don't need to give exact values, you just need to give powers of 10. Okay. Again, it's something physicists love. So whenever you're making a calculation, you want to have some estimate in your mind as to what the likelihood of the size of the answer is going to be. Is it going to be 10 to the power 6, or is it going to be a number less than 10? What makes sense? So you want to check at the end whether you got a number that is close to your estimation. That's called your ballpark, okay? And now we come to the last topic in this chapter, which is types of coordinate systems. We will pick this up again when we start doing vectors in chapter 3. It's very, very important. You would have done this earlier in math, but just to refresh your memory, I would like to go over this again. So we're going to deal with two coordinate systems. One is the XY Cartesian coordinate system, which is given by René Descartes, a French mathematician. It's also known as the rectangular coordinate system. And the other is the polar coordinate system, usually used for rotations. Okay, so here's the first Cartesian coordinate system. Here's my x-axis, here's my y-axis, where the two meet. This is my origin, 0, 0. At any point on this Cartesian coordinate plane, let's say a point P here, is uniquely defined if we know its abscissa and its ordinate, which means its x value, which is 5, and its y value, which is 3. Yeah? And you can do that for any other point. So a given point in general is specified by x, comma, y. Okay, so we just need to know the x and y values to know exactly where it is in the coordinate plane. In polar coordinates, again, our axes look similar. So this is what we call the reference line, which is similar to a positive x direction before. We have the origin, and we have this axis, but this axis is not important. You're going to measure any random point here as its distance, the shortest distance from the origin. So this distance r, if you draw a line joining the 2 points, that's the shortest distance. So the first term that we need is that r, and the second is the angle theta, where theta is measured from this positive reference line direction in a counterclockwise fashion. Yeah? So it's important that you go counterclockwise this way in measuring your theta. So if your line was over here for r, you would measure the entire angle going around this way and not the smaller angle this way. Okay? So we have a reference line, we have a counterclockwise motion from the reference line, and the unique features of a point are given by r and theta. Okay. So to move between these two coordinate systems, let's look once again at this diagram. I'm going to keep this diagram. So my red line stays here, and I'm going to drop a perpendicular here. Okay. A perpendicular to this axis. That perpendicular is basically going to be parallel to this line. And that's going to be the height of this point. That would have been y on the xy coordinate frame. And this distance would be x, right? So we're just going to look at that. So here's my same distance r. Here's the perpendicular that was dropped. This is the length y. And this is the distance x. The coordinates of this point are going to be xy. This x and this y, right? Using Pythagorean theorem, since you know that this is a right triangle, you immediately can see that r squared equals x squared plus y squared. Yeah? And if you use some trigonometry, there are other relationships which can be explored. For example, what is the sine of this angle? So sine is the opposite divided by hypotenuse. That means opposite to the angle, so that's y. Y is opposite this angle. Y divided by r, which is the hypotenuse, right, is sine theta. Here, sine theta equals y divided by r. What's cosine of theta? Cosine is adjacent side. That's this side, the adjacent side. And this is the hypotenuse. So it's x divided by r. Okay, so cosine theta is x divided by r. And then you can write tan theta, which is sine theta divided by cosine theta, which is also perpendicular over adjacent, which is y over x. Okay, so we're going to use all these relationships many, many times and in different ways. You need to be able to do this from a triangle. Okay, so here we are relating the polar coordinates r and theta to the Cartesian coordinates x and y for this point. Yeah? Okay. Here's the Pythagorean theorem that applied there. R squared equals x squared plus y squared. And if you want to find the angle, what we will usually do is we will do tan inverse of both sides. So we'll do theta equals tan inverse of the y component divided by the x component. Okay, we will come back to that. Except when you're doing tan inverse in your calculator, you want to be careful about whether your mode is in degrees or in radians. So if I do tan inverse, this is not a negative sign, this is just a bullet point. Tan inverse of 0.5774, if I'm in the degree mode in the calculator, then I'm going to get an answer of 30 degrees. And if my calculator is in the radian mode, I'm going to get this answer here, 0.5236. And the calculator is not going to tell you that whether this is radians or it's degrees. So it'll just throw up a number, 30.0 or 0.5236. And if you're not careful about your mode, you are going to get the wrong answer, most likely. Okay. So to move from known polar coordinates r and theta, okay, you can use these trigonometric relationships. So if you know r and you know theta, you can find y. Y is going to be basically r sine theta, and x is going to be r cosine theta, right? I'm just rearranging terms there. Okay, so x is r cosine theta, excuse the question mark, and y equals r sine theta. So this doesn't exist. This is x equals r cosine theta. This is how you go back and forth between the two coordinate systems, okay? So let's do a problem on this, and that'll bring us to the end of this chapter. An airplane travels a distance x equals 4.5 times 10 to the power 2 kilometers. That's this distance, due east. Okay, so it's often helpful to make a little compass. That's our starting point right at the origin or center. This is east, west, north, south. So we're saying due east, it goes in this direction. You can draw it parallel over here. And then travels an unknown distance y due north. So this is due north. We don't know this distance. We're going to write it as y. Finally, it returns to the starting point by traveling a distance r equals 525 kilometers. So it returns here 525 kilometers. How far did the plane travel in the northerly direction? So this is what we need to find, right? We need to determine the value of y. What can we use to do this? Right, we could use the Pythagorean theorem. R squared equals x squared plus y squared. Then we would probably need to square both sides and solve for y. So that's what we see here. R squared equals x squared plus y squared. We're going to solve for y. So we take y to the left-hand side. Y squared equals r squared minus x squared. We're going to take the square root to get y. So y equals square root of r squared minus x squared. Put in the values now. R is given as 525. X is 4.5 times 10 to the power 2. Both are in kilometers. So our result is also going to be in kilometers. Okay. So we have 2.7 times 10 to the power 2 kilometers. And that's how you find this value. This is a simple algebraic problem using trigonometry, right? And using right triangles. So you do need to use Pythagorean theorem. And I told you at the start of this chapter, watch out for how many times we use it. So in general, when you want to solve a physics problem, like you have your homework problems already assigned to you, so you want to go to WebAssign and start doing the homework for chapter 1. you're going to start with a rough sketch of the problem. So you read the problem and you try to draw out whatever you can, okay? Label whatever you do know. So the distances, for example, in the previous problem, you would make a sketch like this. Not at all important to sketch the airplane. You could just make a line. Then you're going to write down the values that you know. So you would write here 4.5 times 10 to the power 2. This would be 525 kilometers. You're going to write what you don't know, label what you're looking for. So you're going to label this Y and maybe put a question mark that this is what you're looking for. Then you're going to think of a relationship between what you know and what you are looking for. So you're going to think of a relationship between these two, which are your known quantities, and this, which is your unknown. In this case, just the diagram suggests to you that you're going to use Pythagorean theorem, right? Substitute the known values in the relationship. Once you have the relationship, you then just need to rearrange for the unknown quantity, which is what you did here in this line. And then you substituted the values in this line, right, to get an answer. Once you get your answer, you want to check that your answer makes sense. Okay, so you've solved for your unknown. You then want to check, do the units match? So how do you know what that distance was? It was in kilometers because all the numbers were given to you in kilometers. Does the answer seem reasonable? So you want to think about the order of magnitude. Is the sign meaningful and appropriate? So if you go back to the question, in a square root, you could have had a positive or a negative number here. So the negative number makes no sense. Negative number would mean they're going in the opposite direction, and that means going south, which is clearly not the case because they told you the plane was going north. So you want to take the positive number. What else? They told you if you had come out, let's say, with a value 0, then how could you have an X, which is positive, and an R, which is not the same as X, and yet have a 0 value for Y? It would not be possible for a triangle to be formed like that. So you know that you have to get some positive number. Everything's in kilometers, so it's going to be in kilometers. Okay, that's how you check your results. And with this, we come to the end of chapter 1. Now you should do your homework. Thank you and goodbye.